Hello students, good time to all. I am Chandan Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss Stefan-Boltzmann law and its thermodynamic proof. Let's begin. Statement of Stefan-Boltzmann law. The amount of energy of thermal radiation emitted per unit time per unit area of a perfectly black body is directly proportional to the fourth power of temperature of that given body. Mathematically, E is directly proportional to T to the power fourth, whereas E is the amount of energy of thermal radiation that emitted per unit time per unit area of a black body, and T is the temperature. We use the proportionality constant sigma. So, E is equal to sigma T to the power fourth, whereas sigma is called the constant of proportionality, which is called Stefan-Boltzmann constant, and the value of that particular constant is equal to 5.67 into 10 to the power minus 8 watt meter minus 2 Kelvin minus 4. Sigma is equal to E divided by T to the power fourth. So, unit will be, this is the energy emitted per unit time per unit area, that is watt into meter to the power minus 2 T to the power 4 in the top denominator side. So, it will be K to the power minus 4. It is a number you can easily remember like this: 5, 6, 7, 8. 5.67 into 10 to the power minus 8. What that law signifies? When we consider a black body, let that one is a black body. That black body at a given temperature T, the thermal radiations are incident on that of black body are totally absorbed as we consider a perfectly black body. From the previous video, as we discussed, in case of Kirchhoff's law of radiation, a good emitters are good observers. Since it absorbs all the thermal radiations, so it emit that thermal radiations. The thermal radiations are also emitted from that of black body. The thermal radiations are absorbed and thermal radiations are emitted. Let me consider one unit area of that particular black body. So, how that amount of thermal radiations emitted are depend upon temperature. As we studied, purely temperature dependence is the black body radiations. So, how it is related to that temperature? It is an experimental law, means it is verified experimentally by the scientist Stefan. E, that is the amount of energy of thermal radiation emitted per unit time per unit area is directly proportional to the fourth power of that of temperature. Okay. Later on, that law was thermodynamically verified by Boltzmann. Boltzmann was the student of Stefan. Due to the contribution of Boltzmann in that of law, we call it as Stefan-Boltzmann law. Let we discuss how Boltzmann prove that law thermodynamically. Thermodynamic proof. First, you have to clarify the thermal radiations when incident on a metal or in a body that execute pressure, and these thermal radiations possess some amount of energy just like that of a gas. To be right, since the black body radiation exert pressure and possesses energy just like a gas, they behave like a gas. As the thermal radiations or the black body radiations are behave like a gas, we can use Maxwell's thermodynamic relations as well as the laws of thermodynamics for black body radiations. Thus, the laws of thermodynamics and Maxwell's thermodynamic relations can be applied to a black body radiation. As just like a gas, just as in the case of a gas. Okay, let we prove that law by using Maxwell's thermodynamic relations and laws of thermodynamics. Let capital U the total energy of the radiation, and capital E the energy density of radiation, that energy density of radiation inside a uniform temperature that enclose at temperature T and volume let V. The enclosure having volume V and temperature T. So, E be the energy density of that of radiation. Therefore, total energy U is equal to energy density into volume, equation number 1, and as we say the thermal radiation exert pressure. So, what will be the amount of pressure? So, pressure P is equal to 1/3 of total energy of radiation. We can prove that relation in upcoming videos. Okay. The pressure exerted by the thermal radiation is equal to 1/3 of that of total energy of radiation. Now, from Maxwell's relation, as del S by del V, T as constant, is equal to del P by del T, volume constant, where S is the entropy. Let multiplying T on both sides. So, T del S divided by del V, constant temperature, is equal to T del P by del T, constant volume. Here multiplying T on both sides, T del S, which is equal to del Q from second law of thermodynamics. So, del Q by del V at T is equal to T del P by del T at V, whereas del Q is equal to T del S from the second law of thermodynamics. And equation number 3. From first law of thermodynamics, the value of del Q we can get again from first law of thermodynamics. Del Q is equal to del U plus P del V. The amount of heat supplied to a system is used in change in internal energy, so work done. Or let we divide del V on both sides. So, del Q by del V is equal to del U plus P del V divided by del V. So, del Q by del V at constant temperature and that term at constant volume. Okay, therefore del Q by del T del V at constant temperature, that is the expression for T del P del T at constant volume, that is T del P by del T at constant volume is equal to del U by del V del U by del V, sorry, since we consider at constant temperature, that side also taken as at constant temperature. Here del Q by del V at a T del P by del T and del U by del V at constant temperature plus P. Del V by del V at constant temperature. That is from equation number 3. We put that value from equation number 3. We have del Q by del V is equal to T del P by del T at constant V. Okay. Now it can be simplified. T del P by del T at constant V is equal to del U by del V constant T plus P, or del U by del V del U by del V at constant temperature is equal to T del P by del T at a constant volume minus P. That equation number 4. As you know, U is equal to E into V, therefore its differentiation du by dV is equal to E, and P is equal to 1/3 E. So equation number 4 becomes, so equation 4 becomes del U by del V, del U by del V, that is E. So E is equal to T del P by del T. If we differentiate it with respect to T, so we obtain, that is 1/3 T del E by del T minus, in place of P, 1/3 E by 3. Now it can be easily solved. Therefore E plus E by 3 is equal to 1/3 T 1/3 T del E by del T, that is equal to 4/3 E, which is equal to 1/3 T del E by del T. 3 cancelled out. So, therefore E is equal to, therefore is okay, first we write it, 4E is equal to T del E by del T. If we exchange it as del E divided by E, del E divided by E, so it will be 4 into del T divided by T. Now integrating both sides, integrating both sides, we have that integration over del E by E is equal to 4 integration over del T by T. Its integration, that is log E, which is equal to 4 log T plus a constant, let that constant be sigma, or log E is equal to, here log T to the power 4th plus that constant we can write as log sigma, log A plus log B, which is equal to log AB. So log E is equal to log sigma into T to the power 4th, log cancelled out. So E is equal to sigma T to the power 4th, that is nothing but our Stefan-Boltzmann law. This is Stefan-Boltzmann law of radiation. Now it is proved. So here with the help of this video lecture we understand the concept of Stefan-Boltzmann law. It's an experimental law and that can be proved by Boltzmann. This is the thermodynamic proof. First we relate to that of gas and use Maxwell's thermodynamic relations as well as laws of thermodynamics, and finally we derive that law E is equal to sigma T to the power 4th. So with this useful and informative notes, let me wind up the session. Thank you.